Today, my webinar talk is on enhancing finite element analysis with digital image correlation test data. And like Shelly said, my name is Matt Sanders. I'm a test engineer here at Stress Engineering. There's my picture. Having the buzz cut is definitely an advantage during quarantine because I could still get my hair cut. So that's been something I have going for me. But I'm really excited to talk to you today because we have some new capabilities within Stress where we can get a lot of very cool, very meaningful data out of the tests that we run. And so to go over a little bit about the agenda, I'm first going to give an overview of stress engineering and what we do in terms of analysis and testing. It's really hard to do because stress does a lot of different things. So I'm going to try and move through that quickly and then kind of give an introduction to how do you evaluate the structural mechanics and material response of components and structures. And I'm going to introduce kind of a really good tool for that called digital image correlation. I'm going to show you an example of how NASA uses it. Then I'm going to go into a lot of examples of how we've used it. Can't go into everything that we've done with it because a lot of it is proprietary, but there are some examples that are okay to share. And this talk is kind of based on a talk that I gave at a space symposium conference for the Space Foundation. And so you can actually find a paper and modified presentation from this on the spacefoundation.org's website. So first, to give a little intro to Stress Engineering, we were founded in 1972, and we do a lot of different things in a lot of different industries. So we work in oil and gas, energy, offshore wind, medical devices, consumer products, packaging, aerospace, automotive, and we have a variety of different engineering disciplines. Kind of all the physical sciences are representative. But just to talk a little bit about some of our analysis and design capabilities, we do a lot of complex component design, finite element analysis, FEA, both nonlinear and linear, computational fluid dynamics, stress analysis, creep analysis, fatigue analysis. We work with a variety of different materials, metallics, composite, polymers. We have experts in fracture mechanics and failure analysis, material selection criteria. We even do human factors and thermal analysis. So this slide is just kind of some animations of the type of analysis that we can do. These are kind of some of the cooler videos I was able to pull out. We have a variety of different things that we've conducted, but we can do dynamic impacts like this bird strike on F-35 glass, human factors in terms of how forces are imparted on a body or even a big structure like an airplane or a landing gear. Here's some examples of kind of advanced manufacturing and thermal modeling and simulations that we can do. So a lot of people have heard about additive manufacturing. We can model how a laser powder bed fusion part is built and looking at the total displacement of different components as it's being built with the laser, or a wire arc directed energy deposition technique. We can look at the thermal gradients and temperature as you lay down beads, different effects on the plastic strain of elastomeric materials during like a molding operation, battery thermal management analysis, looking at how batteries can interfere with each other or conduct heat to each other, which is a really important part of our lives nowadays and a big safety component. We do analysis, on quenched forgings and how that can affect the material properties. Besides analysis, we also do a lot of testing. So here's some images from some of our full-scale testing laboratories. Got laboratories in Waller, Texas, Houston, and in Ohio and Singapore. So we can apply loads from a fraction of a gram all the way up to 10 million pounds. We can do material coupon characterization tests to fatigue loading, corrosion, chemical exposure, friction and wear testing. We've tested burst tests on like a shampoo bottle, all the way up to risers and drilling connections. So we have a lot of capabilities, and we can do a lot of customized test setups. So, actuator wear tests or impact tests. Here's some environmental chambers. This is a photo of some custom pressure test setup, actually on a shock and vibration table. We do a lot of environmental testing at high temperatures, flame, fire tests, from very high temperatures down to cryogenic testing. In connection with our test labs, we have a measurement and control department that is highly advanced in creating sensors and instrumentation in order to capture how our test articles respond to the loads that we put on them. They do a great job of coming up with the right data acquisition systems, software, control of different testing frames, and we can do that both in our laboratory and out in the field. We also have a material science department that's great at doing failure analysis and investigations to determine why something has failed and what were kind of the contributing factors to the failure of a part. When they have their own lab, a picture of our creep testing facility, and we can do scanning electron microscope images and metallography in order to help determine what are some of the contributing factors to failure. And so it allows us at Stress, one of the great things about working at Stress is we can take a full multidisciplinary view of how to solve problems, from design to analysis or mathematical modeling to empirical testing and real physical test setups, then to the material science behind it, to failure analysis, to really get a 360-degree view of how things work. So for our talk today, want to talk about enhancing finite element analysis and kind of the link between the analysis and the testing that we do. And the analysis has really taken off. As I've been told, finite element analysis used to be conducted with punch cards. I have a picture of one here from our company a couple years ago. And thanks to the advancements in the computer power capabilities, we can now analyze very complex shapes and structures, and even advanced manufacturing techniques. We can come up with very optimized shapes. However, optimized shapes are very complex, and in order to analyze them, very complex analytical models need to be developed. And so the question is the model right? How can you check your answer? There's no solutions manual out in the real world on if your model is correct, and you don't really know if it's conservative or if it's unconservative. Is it too conservative and you're losing performance, or is it unconservative and you have a level of risk built into that component that you don't know about? And that uncertainty is all kind of driven by certain modeling assumptions that you go into your model. Was it built with the right geometry? Are you properly accounting for the modulus of the material that you're using? Is there any anisotropic behavior? Are your boundary conditions modeled in the right way? And so proper validation of these finite element models is needed. Now, I'm not a FEA guy. I'm a testing guy, so I'm a little bit biased towards the testing side. But testing in the real world environment can give you a lot of answers to what kind of assumptions you should make in your modeling. And there's, I'm not the only one who thinks that. There's some quotes here I like. The American Society of Mechanical Engineers Guide for Verification and Validation of Computational Solid Mechanics has a quote that says, "Scientists and engineers should be aware that the computational models they develop and use are approximations of reality, and that these models are subject to the limitations of available data, physical theory, mathematical representations, and numerical solutions." And there's a paper by NASA on the observations of the current status of performing FEA that says engineers are becoming increasingly efficient in building complex 3D models of complicated aerospace, or really any types of components. However, the current trends demonstrate blind acceptance of the results of the finite element analysis. And it goes on to say, analysis of any physical problem needs to be subjected to verification and validation. And so the question becomes, well, how do you do that? So typically, using empirical test data is a good way to help validate those models, and something that you can compare to your finite element analysis to see what differences you're getting. And so there's a number of different sensors that are used for measuring the material structural response. And the three main types are a foil rosette strain gauge, like shown here. This is a triaxial strain gauge that can be used to calculate out a von Mises strain equivalent under the gauge location. And this is a fiber optic strain. This is a extensometer. It can also be used to measure deflection, typically used in material coupon test. But each of these sensors have some of their own issues and complications. You know, the first off being that each of these sensors only measure in discrete locations. So if this was a finite element model that we had a real world test we were trying to conduct on, we would need to pick different points before testing to try and take strain measurements from to compare to our analysis, and we would just kind of hope that we get them in the right place. And that's another kind of issue or drawback is the installation. You may not get the gauge in the exact location that you want. So if you're trying to pick up peak stress here kind of as a result of this hole, but the gauge is kind of laid off of there, you may not be getting the data that you think you're getting. And also the principal direction is important. So the gauge may be in the right location, but if it's in the grid rosette is in the wrong direction, you can get data that's not correct or different than you think. And the installation is also somewhat timely and costly. Each gauge or sensor or extensometer needs to be attached to the location that you need it. And the more and more sensors that you use, the more timely and costly it is to install them. These sensors also have limitations. So there's only so much range that strain gauges can sense before they become inaccurate or broken. They have a certain finite grid length, so you can only measure over a certain amount and you don't get the actual strain underneath that measurement location. You get an average of that. We'll talk a little bit more about that. And also these sensors have to contact the surface, and sometimes that can disrupt the measurement that you're actually trying to take. The sensor can actually contribute to the behavior of the test article. And so there is a new, somewhat new system that kind of addresses all these issues, and that's called digital image correlation. And the DIC, the way DIC works is you have a test specimen that you paint with a black and white stochastic, which means random speckle pattern of black and white dots. And you have two cameras in stereo that film an area of interest, much like your eyeballs kind of see, that can pick up three-dimensional movements. And so the images from these cameras are fed into a software that then is able to track the movement of those speckle patterns, and you get a color contour plot, much like you get from an FEA analysis, but it's the actual real world how the physical part or test article is moving. And so you can get a three-dimensional strain field, or you can also do point tracking, like this is measuring how this wrench is opening up, and you can really be able to see how the material is behaving across the entire part that you're viewing. So just an example, quick example, how NASA uses this. This is taken from a paper by NASA Langley. They do a buckling test of rocket body structures that are very large. And so in the upper right is the results of a finite element analysis as they apply compression from the top pushing down on these thin wall cylinders. And then down below is the real world measured finite element analysis. And you can see that they match up pretty well. I would imagine that some of the results of the digital image correlation measurements were used to reiterate the finite element model in order to get a better prediction. So now I'd like to go into some examples that we have at Stress, and starting off with a very simple one, just a simple uniaxial tensile test of a 6061 aluminum coupon. So I have a linear finite element analysis here on the right, and the results of the digital image correlation on the left. And we can actually develop movies of how the loading increased, the sample is moving upwards as the load frame pulls on this component. You can see how the strains develop. One thing to note is that the software can actually track very large displacements past the necking region that happens. And even once the sample breaks, the software recognizes the rigid body motion. You can still see the deformation even after the sample's broken. And we can pull out all kinds of data, which we'll go through during this presentation, but one of which is this is a stress strain plot. And this dashed red line is the data from the extensometer, which is shown right here. It's kind of a traditional measurement for getting strain or extension data. However, in a material testing lab, that clip gauge had to be removed in order to prevent it from being damaged during the failure. Well, with the digital image correlation, that's not an issue since there's no contact. So the DIC can actually continue to monitor the strain all the way up to and past failure. And one of the neat things is, because we're getting a full field representation of what's going on, we can, after the fact, come in and go interrogate different parts of what we saw. So we won't just get a single value, but we can draw section lines like this blue section line right down the middle of the test article. And we can compare that to FEA. So at very low levels of load, the linear analysis correlates very well with the DIC, which is what we'd expect. However, up at higher loads, in this case, 24,000 pounds, we can see that in the necking region, the model doesn't do a very good job of predicting what the material behavior is supposed to be. And we can see that compared to the DIC data here in red and the finite element analysis data in the dashed red line. So another good representation of this is welds. So welds don't always end up in the exact geometry that you think they will be, or it's hard to predict. So here's a weld sample coupon where you can see a cap and a root, and there's some high-low difference between these two. And what that does is it introduces a lot of bending into the test sample as it's being pulled. And there's a lot of different ways that you can model this. You can even go as far as trying to incorporate the misalignment between the two pieces into your finite element model and get some very similar results. But once you have the digital image correlation data, you can feed that back in to your model and update maybe your boundary conditions, which end is fixed, or your actual geometry, or even your material behavior. So here we have a plot of the different points that we can pick out and pull out from the actual test data and plot that. Here it's plotted axial strain as a function of essentially time. This yellow line is the applied axial load. And so this data is very telling of what's going on. First off is the coupon, the material doesn't yield or deform evenly. And there is concentrations around the toe of the weld. And so that data can definitely be fed into a finite element analysis to update how that model predicts the different stresses that are going on there. And that can be very useful in terms of things like life fatigue prediction. And I have an example of that later on. So, here's another example, kind of moving away from metallics, but also, it's material independent. So this is a carbon fiber composite tube with kind of a stress concentration cut out hole in the middle. And what this test setup is we had fixed ends, and we applied load at two locations at about 150 pounds force. and then we used a finite element model to predict what the deflection of this carbon fiber composite tube would be. And what we found is that the FEA model, at least the very first run of it, did not accurately correlate to what the empirical test DIC data was. And what this highlights for me is that even a simple, 4-point bend test may not be exactly, or definitely is not going to be exactly perfect like we think things are in the modeling or finite element analysis world. So this is perfectly symmetric. It's assuming the loads are being applied perfectly in a single plane. However, in actuality, the way the test setup, there were some artifacts from the test setup that induced a little bit of torsion and eccentric loading into this part, and actually failed by localized buckling. And this is a photograph of the failure, which the DIC was able to pick up the stress concentration even before failure. And so these types of structures, even though it's a simple geometry, it can be very complicated to model in terms of the different layers of fiber and resin components. So, moving on to another kind of example of a difficult to model or difficult to test component. This example is an additively manufactured alloy 718 part that has a lot of complex geometries, kind of a converging and diverging nozzle with lots of cutouts and different geometrical features. And this was 3D printed on a Renishaw machine by our friends at Kunst Godwin and Tech Labs. They did a really great job of making this part for us, and so that we can test it and get some data out of it. So the test that we did is on the top half. This part was symmetrical. We applied our stochastic pattern of black and white speckles in order to get some DIC measurements. And on the bottom half, we applied what would be a typical strain gauge empirical test setup, where we pick out different locations to apply strain gauges in order to get strain measurements. And the application of this DIC speckle pattern paint took probably about 10 or 15 minutes, whereas installing all of these strain gauges, took over a day. Definitely, 12 to 14 hours of trying to get these gauges installed properly. So this slide shows you a comparison of what the finite element analysis looks like on the top to the digital image correlation. And the first thing that stands out is that they look pretty similar. The stress gradients are in the same areas. The DIC maybe shows a little bit higher peak strains compared to the finite element model. So this might tell us that, hey, maybe the FEA is a little under conservative. It looks like maybe the boundary conditions are in the right spot and being applied correctly, because the contours are similar, but maybe they're just not magnified enough. Maybe the material representation in the model is not accurately representative of what this additive material really responds like. Something to point out here is, so if we were to just look at the strain gauge data, all we would get is single values of microstrain at the different locations that we wanted to interrogate before the test. And that's not as much data as you can see as compared to a full field color contour plot. Another kind of disadvantage of the strain gauges is if we were to, say, want to compare this area to our finite element analysis and put a strain gauge right there, excuse me, sorry about that. If we were to put a strain gauge right there, that strain gauge would read a constant reading, just give us one value right there at that location of, let's say, 400 microstrain. However, in actuality, when we pull off the digital image correlation data, we can see that there's really a high stress gradient right there in that location, which is maybe more representative or more comparable to the FEA. But the strain gauge, it just gets an average of the strain underneath where that gauge is bonded. So that's kind of an advantage of how DIC can be used to get a better resolution, a better understanding of your data during a test in order to better update your finite element analysis. So this is an example of another kind of complex additively manufactured part that had a lot of internal cavities, a lot of flow restrictions, a lot of internal tubes. This was actually printed by us by Oerlikon. They do a lot of great work, and we applied a compressive load of 80,000 pounds kind of coming down from the top, and you can see how the strains are developing as that compression load is increasing. And so we even get, you know, a three-dimensional representation of what that part looks like as it's being loaded. And so this slide will show us what the digital image correlation from that test looks like compared side by side with a finite element analysis. And some things to note is that generally we get a lot of the peak strains and strain gradients in the same areas, but there are a little bit of differences. So, you know, the DIC data shows kind of a peak strain flowing down this way, where in the FEA it kind of shows it going up. So that can maybe indicate that maybe our boundary conditions need to be adjusted, or maybe there was something in our testing setup that wasn't matching the perfect finite element model boundary conditions. You know, also the material response needs to be looked at to see how the model assumes the material is going to behave. So moving on to this next example, this is a pressure vessel looking at the stresses in a dented pressure vessel. This is actually a aerosol can that had 2 dents in it right here. And so we were able to measure the strain due to pressure inside this aerosol can, and that's represented over here on this photo, or this contour plot. And we can draw section lines at different areas of interest and then plot them. And so what we can see is that that dent location caused a peak strain of approximately 12 times the pressure or the stress in the base of the can. And so this is helpful for if you have any kind of damaged components or damaged pressure vessels and you want to know how has that damaged or dent affected the strain being seen in that material, how's that going to affect the fatigue performance of fatigue life? You can directly measure that here visually with the DIC software. So we also looked kind of further up on this aerosol can, and to the eye, you could not see that there was a longitudinal weld in this can. However, in the data, you can see a concentration of strain due to a weld seam. And so that concentration of strain was actually twice that in the bulk base stress of the can. So we actually went out to a refinery and looked at some pressure absorption vessels and was able to measure the strain concentration due to the welds on these large pressure vessels and use that to get a better understanding of what the fatigue life prediction models should actually be factoring in these strains. And what another advantage of that is we were able to find, once we looked up and down this pressure vessel at the welds, we were able to find the areas that had the peak strain concentration. And from then on, we knew that if we ever needed to go back and inspect those welds, that would be the best place to look first because it's where the highest stress concentration is. So this next example is something similar. It's a pressure vessel that has a girth weld in it and a cutout simulating some corrosion. And it also has even a defect that was machined into it to simulate a crack. So this is a test article that we did where we were trying to simulate corrosion on the outside of a pressure vessel and also the start of just a crack tip. And so we applied tension and internal pressure to this vessel and then also watched it with the digital image correlation, and we can get all of this data out and then use it to create better prediction models of how this type of defect and this type of corrosion loss will affect our finite element models. It's something that is very hard to get this type of data with traditional strain measurement techniques. One, because we get a lot of elongation of the sample because we're going all the way to failure, and there's a high stress gradient. So any strain gauge that we would put kind of in this area would only pick up an average underneath it. But with this DIC technique, we can get the full field strain and use that to update the finite element modeling predictions of this particular component. So this next example here is a pipeline that had a dent in it, kind of similar to the aerosol can that I showed you earlier, but this is kind of a bigger example. You know, pipelines, whether they're buried or subsea, can sometimes be damaged by a backhoe or an anchor or maybe a dropped object. And so what this data shows is a dent. You can kind of see the dent there and the curvature of the pipe. And we were conducting pressure up and pressure cycles on this dent. And as the pressure increases, you can see how the strain concentration develops because of this dent. And it's definitely a concentration. It's much higher than what the base pipe or the area unaffected by the dent away from the material is. And so that needs to be accounted for in any kind of modeling or prediction of fatigue life for this pipeline. So kind of moving on to a summary here, we talked about that there is a need for proper finite element analysis validation because there is a number of analytical assumptions that go into those models, in particular geometry, which may or may not be correct or representative of the actual real world geometry. We saw that example in the welding coupon. There's assumptions about how materials behave and whether they do or do not have isotropic behavior. And this can be particularly important when looking at composite materials or new materials such as those that are used in additively manufactured components. We looked at the importance of boundary conditions and how they may or may not be representative of real world conditions, like that composite tube. The testing of that was not exactly perfect in the loading conditions, but the DIC data was able to pick up on that and use that. Same with the loading conditions. And we talked about there's difficulties in correlating test data. There's limitations in sensing instruments like strain gauges. Also, materials do not deform evenly or perfectly. So even though you might have a constant cross section, if you put a strain gauge there, any type of axial load or bending may not be representative of the full thickness or full cross section of that part. And, you know, the real world does not have perfect geometries or loadings, and buckling loads, bending, torsion can be difficult to predict and also difficult to apply in laboratory conditions. High stress gradients are difficult to measure, and these high stress gradients are a result of actual real world features like welds and ribs, holes and transitions that are a part of, you know, pretty much every component that's out there. And anisotropic material properties need to be accounted for. And so, you know, finite element analysis and testing and DIC all have limitations individually. At Stress, I feel like a combination of proper testing methods, using the full field digital image correlation and strain gauge data, along with FEA, can provide the best opportunity for understanding how complex materials or geometries perform under load. And I really do think it's this combination that leads to a better understanding of how components behavior can be predicted or used, and that leads to either an increased performance of the component that you've done analysis and testing on, and a better understanding of the risk of that component either breaking or underperforming based on the given criteria. So with that, that's my presentation, and I really appreciate everybody listening in and like to open it up for any questions.